So, hi everybody to today's session of the probability seminar in Chile. It's my big pleasure to introduce Sahar Diskin, who is from Israel originally. He did all his studies in Tel Aviv University, but now he's a postdoc, so he's Hermann Weil instructor officially at ETH Zurich. And he did already quite some remarkable work, both in combinatorics and probability. And recently he's also working on percolation. And today he'll talk about this result in percolation, namely supercritical sharpness in percolation. So please, Sahar, go ahead.
Thank you very much, Dieter. Thank you for the invitation. Thank you for the kind words. So yeah, we'll talk about supercritical sharpness. Before I start, just let me say that if anything is unclear, if you have any questions, any comments, just feel free to ask and interrupt me in the middle of anything. Just feel free to do it. And everything I will talk about is joint work with some amazing colleagues, all of them here at ETH. So Philip Easo, Ritvik Ramanan-Radhakrishnan, Benny Sudakov, and Tassion. So you can see them, some more enjoying life and some more enjoying teaching or other activities, but that's all of them. So that's Ritvik, Philip, Vincent, and Benny. And yeah, the talk we'll talk about percolation, and let me just, sure all of you know it, but let me explain what I mean when I talk about percolation. So the model is the following. I consider some host graph G with vertex at V and S at E. So for example, this blue creature that we have here. And when I talk about P percolation, I consider P percolation on this graph. I just put a dice or flip a coin for every edge independently, and with probability P I retain it, with probability 1 minus P I throw it out. So then I get this P percolated random subgraph. And in more probability type of words, I can say that I just denote by P subscript P the standard percolation measure. So every edge is open with probability P and independent of the others. And I originally come from, my research started from combinatorics and probabilistic combinatorics. So one place where we see this model quite early on in our interaction with it is in the classical binomial random graph GNP. Due to Gilbert, what I will talk about now is a result of Erdős-Renyi on a similar model. So this is exactly the same as doing P percolation on the complete graph. And one stunning thing that you consider, so you can see, look at simulation of a graph on 1,000 vertices, and here the probability is slightly less than 1 over 1,000, so less than 1 over the number of vertices. And what you see here are the connected components, the clusters. You can see that all the clusters are quite small, and I have here plenty of isolated vertices and some edges, but everything is very, very small. So this is when the probability is less than 1 over n. But then if you push the probability slightly above, the image changes drastically. So now I percolate with probability slightly more than 1 over 1,000, 1 over the number of vertices, and there emerges this giant connected component, beautiful structure. In particular here, everything else is very, very small. So this is one image that we see, but of course, if you come from probability, maybe first you will see it when you think about the lattice. So for example, on Z squared, Z squared. But here you have the same image, right? So if you think of the probabilities being less than half, then all you have are these very small connected components. You see them here in different colors. And then when you push the probability slightly above half, you have this infinite component. So now the graph is infinite. So it's an infinite component, this yellow thing, and everything else is outside of this infinite component is much, much, much smaller. And in this talk specifically, we'll be interested in percolation on infinite transitive graphs. So our graph throughout will be infinite, connected, transitive. Transitive means that every vertex looks the same. So for example, this includes, of course, the complete graph, lattices, but many, many more creatures, the hypercube, etc., many, many more graphs. And given such a graph, we can define the critical probability. So this is the infimum over all parameters P, such that the probability that the origin is connected to infinity or managed to reach infinity in this P percolation is strictly bigger than 0. And this is exactly the point of this phase transition that we saw before. So below PC, for any parameter below PC, we call it subcritical. And most surely, that is with probability 1, all the components are finite if I do percolation on this graph. And above it, this is what we call the supercritical regime. And most surely there exists an infinite component. So we have this beautiful phenomena happening across essentially all infinite transitive graphs. So to show the existence of such a PC, critical probability P is not very hard. It's also not very hard to show that it's bounded away from 0. And essentially for connected transitive graphs, it's bounded away from 1 if it's not one-dimensional in some sense. So it's well-defined, and for pretty much any graph that you can think of that's interesting, it's something strictly not 0 or 1. You can really think about it. And when you see these beautiful phase transitions happening, there are two very natural questions that come to mind. First of all, what happens exactly at PC? And that I won't talk about. That's one big conjecture. The other thing is, okay, so I see that before this critical probability, all the components are finite, and then afterwards I have this very strong phase transition, the emergence of an infinite component, and I can ask, how sharp is this phase transition? So what do I mean by how sharp? In some sense, I want to understand how fast does this happen. And one way to quantify it is the following. So if I look at the subcritical regime, and I will call this subcritical sharpness, so I can ask myself, how strongly finite are the finite components? So what do I mean by how strongly finite are they? So I look at this image, and I look at the subcritical one, and I fix some vertex to be the origin. So this is this red vertex here. And then I consider the component of this origin, and I ask, what's the probability that it is bigger than a particular size, that I managed to reach quite a large size? And this is a result of Menshikov and Eisenman and Barsky, and they showed that for any subcritical probability, there exists some constant C such that for all n, the cluster of the origin, the connected component of the origin, satisfies that the probability it's bigger than n decays exponentially in n. So we see it's as sharp as we can hope for. It decays exponentially. The probability in the subcritical regime that I grow bigger than some than size n in the origin decays exponentially in n. And let me just say that it was proven on the d-dimensional lattice, but it's relatively easy to adapt it to more general settings, like as we consider here, infinite transitive graphs. So you have here, for example, several new proofs. There is also this very beautiful modern proof by Dominique Copon and Tassion from 2016. Okay, so the subcritical image is very well understood by now. And the question you can ask yourself, okay, so I understand how fast or how sharp this behaves in the subcritical regime. What about the supercritical regime? So in the supercritical regime, I would want to understand how strongly finite are the non-infinite components. So I know that I have an infinite component, and I fix the origin, and suppose it is not in the infinite component. The question is, what's the probability that the cluster of this origin is still quite large? So in other words, here I would want to understand how large are these holes inside the infinite component? How large can be these clusters that are not infinite? And this is our main result, an answer to this question. And in order to answer it, let me first define the following notion. It's quite simple. So for every graph G, and for every parameter n, I denote by phi of n the minimum number of edges leaving a set S, which is of size at least n, but finite. So I go over all possible sets n, and I look at the number of edges leaving it. And what we showed, so again, together with Philippe Easo, Vic, Van Sant, and Benny, and myself, we showed the following. So for any parameter, for any percolation probability P, which is supercritical, there exists some constant C, such that for all n, the cluster of the origin satisfies the follow. The probability that it is of size at least n, but finite under the P percolation decays exponentially in phi of n. So it decays exponentially in this minimum number of edges that are needed to cut some set of size n. And few comments about this thing. So first of all, this result is tight. So you can show that this probability is at least e to the minus some other constant times the same phi of n. So this is the best we can hope for. And it was known before for particular cases. So it was previously known for the d-dimensional lattice. This proof was by Grimet and Mashran, very influential in the 90s. It heavily relies on the self-symmetries of the d-dimensional lattice. It was extended to graphs, Kelly graphs or transitive graphs of polynomial growth. And this really relied on the deep theory of Gromov and Trofimov about group theory. And it was also known for non-amenable graphs. There they used the expansion and also some deep theory about the groups, non-amenable groups. And as you will see here, the proof that's essentially throughout the rest of the talk, I will explain the proof, the key ideas in the proof. And you will see that it really uses very natural and elementary ideas and generalizes and captures all the previous cases, but also generalizes to any infinite transitive graph. So we don't know anything about the structure of the graph besides it's transitive. We don't assume anything more than that. Any questions about the result?
Do we have, like, for general graph, do we understand well phi n? Or
it could behave, yeah. So for transitive graphs, there are some jumps in how it can behave, but there is a lot of ways it can behave. And for general graphs, it could be even more chaotic. So it's not something we necessarily understand very well. For certain graphs, we know exactly what it is. For other graphs, we completely don't know, but essentially this what dominates this probability. This what dictates this probability. It's some feature of the geometry of the underlying graph.
Thank you.
And really this leads us to, it's a good question, it leads us to the following. So actually what we will prove is, what we'll see today is a slightly stronger result, which says the following. So, and this is almost the last definition we will have, don't worry. So for any finite set S, I denote by pi of S the size of the minimum cut of S to infinity. So this is a deterministic quantity. So I have some set S and I ask how many edges do I need to cut to separate it from infinity, the minimum number of edges I need to cut to separate it from infinity. Notice that it might not be the boundary of S. Maybe it's cheaper to cut somewhere farther away from S. And what we will prove is the following slightly stronger theorem. So the probability that the cluster of the origin is finite, but in order to separate it from infinity, like this pi of this cluster is at least n, this decays exponentially in C of n. So this really relates this to the geometry of the cluster, geometry of the graph itself. And this implies naturally the previous one because pi is at least phi of the cluster, it's at least phi of n. In particular, it implies the same thing. So this is actually the result we will show. Okay, so throughout the rest of the talk, I would like to explain how we can obtain this. And let me start first by explaining the key proposition that we will talk about and how to derive this theorem from this key proposition. So we can see, the key idea here is that many touches suffice. So what do I mean by touches? So, and this is now the last definition, given some graph G and again a finite set S, I denote by T of S the number of edges on the boundary of S, which are connected to infinity without going back to the set S. So for example, this is my set S, and I'm interested in the edges that go to this infinite green component without having to go back into the set S. So I don't care about an edge like here that I have to go back to S and only then manage to go to infinity. I want to be able to directly go to infinity without going back to my set S. So T of S is the number of these edges. Okay, And in order to prove the theorem, we will, we'll derive the theorem from the following proposition. So for any supercritical parameter Q, and for every epsilon, there exists some parameter C, some constant C, such that for any set S, the probability under Q percolation that the number of touches is at least some constant, this constant, times phi of the set, is at least 1 minus epsilon, this constant times phi of the size of the set. So what do we mean by this result? What does this proposition tells us? It tells us that it's not too unlikely for a set to have many touches with the infinite component. So for any fixed set, it's not too unlikely that I will find many edges in its boundary that eventually go to infinity. Okay. And what we want to show is that the first thing I want to show you is why this proposition about the number of touches implies the theorem. So before we do that, any question about the proposition itself? The statement? Okay, perfect. So how does this proposition imply the theorem? So we suppose we have the proposition, so let's choose some supercritical parameter Q, which is between, it's supercritical, but it's smaller than P. And we can also choose epsilon, so we choose epsilon such that 1 minus epsilon is bigger than 1 minus P over 1 minus Q. You can do that. And then we can apply the proposition, and the proposition will tell us, oh, there exists some parameter C, so this is the C that is guaranteed by the proposition regarding the number of touches. And the event that we will want to consider, the key event here, is the following. So what does this event tell us? It tells us, start from the origin, do P percolation, you expose the P cluster of the origin. So you have some P open cluster here, all of these edges are P closed. And then afterwards, in the rest of the world, you continue with Q percolation. Remember, Q is a smaller parameter than P. So I start with some strong parameter, and then I continue at some weaker parameter. And the event is that the number of edges, which after I do this P exploration, the number of edges in the boundary of the cluster of the origin that go to infinity in the Q percolation outside is at least Cn. So this is the image that we want. This is the event that we care about. This is the image we care about. I do P percolation. Outside, I do Q percolation. And I ask what's the event is that the number of these edges is at least Cn. The same C we got from the proposition. So on the one hand, I can estimate this, I can bound this probability from below because we have the proposition. The proposition tells us that up to paying 1 minus epsilon to C times N, to the number of touches, this is the same as asking that the cluster in P percolation is finite, but the number of edges required to cut it is at least 10. This is just applying the proposition and rearrange. Any questions? Is this clear? Okay. And so this is on the one hand. On the other hand, what can we say about an upper bound? So let's look at this image a bit differently. So instead of thinking about it as if I first explored from the origin with P percolation and then continued with Q percolation, I can switch the image. I can now think of this as if I started exploration from infinity with Q percolation, and then I moved, and then I continued. So if you want to formalize this, so you can think of infinity as a point, and you can also think of just taking a very, very, very large ball and doing the Q percolation from the boundary of this ball. And then what do I want to happen? So I do this percolation from infinity, and every time I reach one of these Cn edges, I know it is Q closed, but I also want it to be P closed. So I allow some sprinkling on each one of these edges because now I continue with P percolation, and each one of them has to be closed. Otherwise, it would have been in the P cluster of the origin. So I know they are Q closed, but I also ask them to be P closed. So this costs me 1 minus P over 1 minus Q to the number of these edges. So for this event, on the one hand, looking at it first the exploration from the origin and then continuing with Q percolation, the key proposition about telling me it's not too unlikely to have so many touches for a particular set S. This particular set S is just my cluster of the origin. It tells me this event is not too unlikely. On the other hand, looking from the outside, I get this bound on this event. And now just rearranging, I get the probability that I have the cluster of the origin is finite, but I need at least n edges in order to isolate it. This is at most this term times 1 over 1 minus epsilon to the Cn, and we chose 1 minus epsilon, so this thing works correctly. So once I tell you that it is not too unlikely to have this many touches phenomena, then I can tell you immediately that I can give you an exponential upper bound on this event. Any questions about this part?
No.
Okay, so perfect. So this I should say modulo the fact that we're doing things with exponentially small probability. Like this idea is very reminiscent of this repulsion idea, also used by Hatchcroft in previous paper. And really the key struggle here, the key thing in the paper is to actually prove this proposition. And this is what we will now focus on. So this is really where the new ideas kick in. So what do we want to show? We want to show that for any supercritical parameter Q and for every epsilon, we can find some constant C such that for any set that you give me, the probability that under Q percolation, the number of touches of this set with the infinite component is at least C phi of S, is at least 1 minus epsilon to the C phi of S. Okay. So how can we try to approach this? So we need to fix this supercritical Q and fix this epsilon. And let us also, in order to make things a bit easier, let us fix n and a finite set S with pi of S being at least n. In particular, also phi of the size of S is at least n. So what does this mean? This means that I have a set S here, and in order to separate it from infinity, if I want to have something here that separates it from infinity in the graph itself, it has to have at least n edges. This is what I know. Okay, so let's try to prove this thing. We want to keep getting more and more touches and show that we can get order n touches with not too small probability. So let's start with some toy version. And in this toy version, what we're going to do is we're going to pick some parameter P. It's not the same P as before, it's different P. This P is supercritical, but it's smaller than Q. I know that Q is supercritical strictly above PC, so there is a place where I can fit in P, which is still supercritical, but leaves me a little bit of space to sprinkle in the future. And let me denote by theta the probability that 0 goes to infinity. Okay. And what we know by assumption, because we are supercritical, because P is supercritical, we know this is strictly bigger than 0. So what does this tell us? This tells us that for any vertex that I look at, one of the two things happen. So I know the probability that it goes to infinity is at least theta. So one of the two things must happen. Either it goes immediately to infinity, or it goes first through S and then to infinity. So I have here two events. Either it goes immediately to infinity, or it first hits S and then eventually manages to go to infinity. So every vertex has probability at least theta over 2 to either go to infinity or to go to S. This I know about every single vertex outside of S. Okay. So this, in some sense, splits the entire graph into vertices that favor infinity and vertices that favor the set S. And now what can I ask myself? So let's try by something quite simple. Let's just ask what's the probability we manage to get one touch, at least one touch. So because the graph is connected, I can find not only two vertices like that, but I can find an edge such that one endpoint of it favors infinity, the other endpoint of it favors S. Might be that the other endpoint is already at S, but that's okay with us. So I can find such edge. So thus far, I didn't do anything with percolation. Okay. And now I can ask for this edge to be open, say, under P percolation. If it's open in P percolation, certainly it's also open in Q percolation. So I need to pay P. So now it's P open. Great. And now if I want to create a touch, I also need that this endpoint manages to reach S and this endpoint manages to reach infinity. So for that, I will need to pay theta over 2 squared for both things to succeed. This is an increasing event, so I can do this. And then I managed to get one touch. Okay, that wasn't too ambitious of us, and also this is not that high probability, but we're starting to understand the problem. And let's denote this quantity by alpha. Okay, and now I want to repeat this thing in order to get more touches. But one thing that I have to be careful is that all of the exploration I did thus far is in P percolation. So everything I revealed is in P percolation. But what I have to notice is if I look at this cluster of this edge that I uncovered, I already know that all its boundary is P closed. So whatever I do now outside will be, I need somehow to deal with this negative information that I revealed. And this is why it's good that we picked P to be slightly smaller than Q, because we can fit in some delta such that P plus delta is still smaller than Q.
So
and why?
Sorry, another doubt. We are working with just one infinite connected component?
We are working with, say again?
With just one infinite connected component?
So it doesn't really matter. Yeah, so that's a great question. So I treat here infinity as a single point, a single vertex, but you can just as well think of the following. So I take a very, very, very large ball, and the infinite component for me is whatever I manage to reach from the boundary of this component. So it could also be that there is more than one infinite component, and then the number of touches is just to any of the infinite components. It doesn't matter for us.
I see.
So as far as we're concerned in this argument, you can think of just wiring everything outside a very, very large ball into a single point and calling this point infinity. And by just exhaustion, this argument eventually, this will give you the same thing.
Thank you.
Yeah, that's a good question. Okay, so I pick this delta, and now I can ask myself, I can try to get another touch. So I already paid alpha to get the first touch, and now I will find another edge outside. This endpoint will favor the purple thing, whatever I already uncovered, which is part of the infinite component, and the other endpoint will favor S. And then again, I need to pay for this to be open in P percolation. Then I need to pay for the cluster to actually succeed. So I continue the P exploration of this edge, and I want it to reach both S and also to touch what I already covered. But this thing, I know they are all P closed, but that's not that bad. I still have delta, so I can now sprinkle delta on these edges, and I just need one of the edges to be open. So I get here alpha times alpha delta. So this is at least alpha delta squared. And in general, you can see that now I can repeat this argument again and again and again. So if I want to get T touches, it will take alpha delta to the T. So this is a bit silly, but it already gives us some bound. This is a terrible bound. We want to get something which is exponential in t, but of the form 1 minus epsilon to the t. So we want to be quite close, but we do get here something. So we understand that every time we have to pave to open something, and then we need to consider the cluster, we see that we can iterate it several times. This is the toy version. So what's really the thing that we want to do? So trust me that this gluing thing, managing to glue things together, this delta that we paid, this is not really the key issue. This is not going to be the hard thing. What we really will need to improve is this alpha term. So our goal will be to increase this alpha, which is p times theta over 2 squared, increase each one of these terms to be 1 minus epsilon. So if I can show you that I can find where to start this exploration with probability 1 minus epsilon, and then succeed in finding an actual touch with this exploration with probability 1 minus epsilon, I will then be able, and then to be able to also continue this enough times, then we'll be in business. So we have two goals. First, to not lose this property of being able to continue this experiment. And the second, to increase the probability of each one of these things. Okay, so this is what we want to achieve. And let's try the first attempt for this. So one thing you can try and do is say, okay, let's pick some parameter L, such that 1 minus p to the L is at most epsilon. And then instead of picking one edge, I can pick L many mid edges. I can do this because pi of s is at least n, and n is very large as far as I'm concerned. So, and L is just some number here. P is constant. L is just some number. So I can certainly find some L mid edges in the sense that this endpoint goes to infinity, and this endpoint favors s. And then what's the probability that I manage to get at least one touch? So now I can consider all of these LHS and just ask that at least one of them is open. So what's the probability that at least one of them is open? It's exactly 1 minus p to the L. So I get here 1 minus epsilon, one of them opens, and then I continue the exploration and ask one side to actually reach infinity, the other side to reach s. So I pay here theta over 2 squared. And my question here is, can anyone see the problem? Now I want to do this experiment again. What could be the problem here?
You have too much negative information now, no?
Exactly.
You have negative information, yes.
Exactly. There is too much information revealed. As far as I'm concerned, it could be that somehow this cluster that I revealed, it only gave me one touch, but it revealed so many negative information close boundary of size n. Somehow it enclosed the entirety of S and only then reached infinity. I don't know if it did or didn't do that. I have no idea what's going on outside of this cluster. So too much negative information is revealed. I cannot even repeat this argument one more time. So this is quite a bad attempt to improve them to 1 minus epsilon. Okay. But still, it's not a wasted idea. So let's try something else. Let's first pick some, let's add something additional between P, delta, and Q. So I add some eta, some small parameter that I can fit in between P plus delta and Q. This is some low density percolation. And now I'm going to do something which is a bit different. So usually the sprinkling arguments, how do they work? I first do this thing with the more dominant probability, and then I continue with the, I sprinkle a little bit with the low density probability, pretty much like we had in the moving from the proposition to the theorem. But here I'm going to do something a bit different. So let's pick again some parameter L, but now I ask L to be such that 1 minus eta to the L is smaller than epsilon. So L is much bigger than before, but it's still just a number, it's just a constant. And now I pick L many edges and ask what's the probability that I manage to get at least one touch. So what I'm going to do now, I'm not going to reveal these edges at the parameter P. I'm going to first reveal them at the much lower parameter, at the parameter eta. So I start by the sprinkling. I start with the low density thing. So I reveal them with eta. And I know that because of how I choose this eta, with probability at least 1 minus epsilon, one of them opens, say this one. And then after I managed to find a good place to start my exploration at, and it's a good place because I know this one goes to infinity with not that bad probability, this one goes to S with not that probability, I just continue with the P percolation and ask that this thing happens. So this only costs me theta over 2 squared. And now observe that I can continue this thing because the only information I revealed at P is about this particular cluster. So as long as this cluster did not create too many touches with S, because pi of S is at least of size n, I can still find many new edges and continue revealing them with eta. The fact that I revealed eta percolation here does not affect anything else, or the fact I did P here does not affect the probability of the eta percolation. P and eta are independent percolations. So the fact I first like threw a tiny bit of water to see whether the area I'm looking at is even relevant. And if it is, then and only then I continue with the P percolation. So now we are getting somewhere. So this improved the first thing to 1 minus epsilon. The second thing is still a bit problematic. The second term, we still need to improve it. Okay. So how can we fix this thing? We're still in the same image, but now let's try to be a bit more ambitious. So picking an edge doesn't seem to be enough. Let's try to pick something bigger. So what we know is because the graph is transitive, we know that we can pick an R such that if I look at a ball of radius R around the origin or around any point, the probability that it connects to infinity under P percolation is at least 1 minus epsilon squared. So I can pick R large enough so this works. So if this doesn't work, I will take a larger ball. Eventually, there is some R, some fixed, it's a constant R, depending on epsilon, such that the ball, if I take a ball large enough, I know that this property holds. And if this property holds, then by the square root trick, just looking at these two events, I know that for every fixed point, the ball around it has probability at least 1 minus epsilon to go either to infinity or to S. So I replaced the edges now by balls of radius R. And now I still want to have many chances of success. So I pick L, and now L is going to be huge, but it's still just a constant. So I pick L such that 1 minus eta to the number of edges inside the ball to the L is at most epsilon. So what does this tell us? It tells us that if I now take L many balls and I do eta percolation in each one of them, then the probability that at least one of them is fully open under eta percolation is not that small. It's at least 1 minus epsilon. Okay, so now we're getting somewhere. So I can find L many balls. All of them are well positioned in the sense that they have good probability to go to infinity and good probability to go to S, good meaning at least 1 minus epsilon. And I begin by asking myself the same question as always, what's the probability I manage to create one touch? So as we already suggested, we will start with the low density thing. We sprinkle inside and we ask, can we at least get one of them to be fully open? But by the way we chose L and R, we know that the probability that at least one of them opens is at least 1 minus epsilon. So this ball is now fully open. But if this ball is now fully open, what I can do now is continue with the P percolation. And because of this property, I know that, again, with probability 1 minus epsilon, I will be able to get a touch here. So this is what happens at one iteration. And now my question is, this is great. This is exactly what I wanted to do. My question is, can I repeat it enough times? Remember, the number of times we want to repeat it is proportional to pi of S. Has to be proportional to pi of S. So some constant times n. And the question is, how can it be that I stop this process? I am not able to continue. Is it possible that this happens before the number of touches is at most some constant times n? Okay, and here this is really where this pi of S is going to kick in. So observe that every time that I did this experiment, what happened? I had L many balls of radius R that I tried something on them. Some of them are now waste, some of them are successful, and if they are successful, they also manage to give me a new edge. What does it cost me to actually see that I can no longer continue this thing? So I claim the following holds. I claim that the number of touches that I was able to get, plus the number of eta revealed edges, has to be bigger than n. Why is this true? This is exactly true because of this pi of s. So observe that if I want to somehow have this event stopping, I need to have already revealed under eta percolation so many edges together with the touches, so many edges that I manage to isolate S from the rest of the graph. So I managed to isolate S from the rest of the graph, from infinity. And if this happened, so what does this mean for us? It means that how many rounds did I run? So I ran really successful rounds in which I got so many touches that the touches themselves already separate S from infinity. But in that case, I'm happy. But if this is not the dominant term, then it means that the eta revealed edges, that is the things I have here in these balls, they are the ones that stop this process. But at every round, every iteration of this game, I'm not throwing away too many strings. I'm just throwing away the size of the number of edges inside the ball times L. So if I choose C, in particular, if I choose C to be small enough with respect to L and R, then I'm in business, because it means that every time that I do this round, I only reveal order 1 over C many edges. And the number of times I have to do this is proportional to N. But every time I do this trial, I have good chance of getting a new touch. So either way, I'm happy. Either I had really successful games before, really successful attempts before, they managed to get me to the correct number of touches, or I couldn't halt because I couldn't hunt too early. I had to cover everything with so many unsuccessful balls, but so many unsuccessful balls means I also had plenty of successful balls and proportional to N, many touches. So this is the idea behind the key proof. Let me say one last thing here. So you can see that this is really where the geometry of the graph comes into play. This is where pi really comes into play in this particular question. Can I halt before? And this already tells you that if we go back to the toy example that we had, something was wrong here, because a priori here, nothing stops me before I'm able to cover all the boundary of S, before I'm able to reach every boundary of S, because every edge of this form would still have some probability of, this is already in S, and this has some probability to reach outside. So I will be able to continue as long as I have boundary edges of S. But the boundary of S could be much bigger than pi of S. S could be, for example, some ball, but pi of S would be a box around it if I'm looking at some lattice. So this means that this toy example didn't capture anything deep, really. But here we see already that already the second attempt, I was really blocked by this pi of S, and indeed, in this final argument, I really see this geometry coming to play. And yes, this is all I wanted to tell you. So this is essentially the key idea of the proposition and of the proof. And with that,
Sahar, where did you use delta here? Sorry, I got lost. Where's
yeah,
delta?
so delta, if you remember, delta from the beginning is after I did one of this, every time I do this thing, so we can go back to the toy example, because there we also see delta. It's just used to glue things together. So this is where delta comes into play. So I do, in the final attempt, this will be actually a ball that was successful. And then I find another ball that is successful, and I manage to fill it up. And then it cannot reach infinity. I have these edges here that are closed. So I need to sprinkle delta in order to make them open. But because I know everything happens with probability 1 minus epsilon, this delta is now also 1 minus epsilon. I have such a good probability, it means I have plenty of edges here, not just one edge. So delta is just this gluing parameter.
Yeah, thank you.
Yeah, and that's it. Thank you very much.
So I had a question. So how far is this to work for FK percolation?
That's a great question. So we thought about it a little bit. And one thing I can tell you is that some key parts of this argument can be, don't really need all of this exploration. I can do them using only FKG. I don't need anything more than FKG, which is great if I want to move to FK. But I think the key difficulty is actually in trying to find an analog for this argument that we had here, if we want to do it for FK, for this type of argument. So this is no longer true. Like it's unclear how to find something equivalent to this event. And in general, also, this is one of the key difficulties. Also, like if you change the boundary condition from wired to non-wired, it also changes many of the other things. But I think the first key difficulty is actually here, because this later type of arguments, finding these balls and everything, we are also able to phrase them in terms of, we believe at least, we haven't carefully checked it, but we believe we are able to do them using only FKG.
Another question, you supposed vertex transitivity. Can you do something if there is, say, a finite number of orbits, or like if it's not completely, but say quasi-vertex transitive, can your arguments apply?
Yeah, in fact, the only thing we actually need, we don't really need transitivity. Transitivity is, of course, suffices, but what we actually need is that the graph satisfies that there is some R such that for any vertex, a ball of radius R around this vertex, the probability that this ball connects to infinity is not that small. That's the only thing we need. In vertex transitive graphs, this holds because you just grow the ball and eventually it holds, but it also holds in many other cases. You don't need to assume transitivity. It holds also for quasi-transitive, and it holds for many other graphs. In fact, I cannot think of any reasonable graph in which it doesn't really hold, but yeah, that's the only thing we need to ask of the graph.
I see. Other questions in the room? And you said this is tight for any setup. So it's always a constant times this phi of s. This is phi of n. This is always the no matter what graph it is, it's always tight.
Yeah.
Not just for ZD, but for any graph. The bottleneck is basically the mean cut.
Yeah, any transitive graph. So to see the other direction, like to see the other side of this. So, for example, you can look up the paper of, there is this very beautiful paper by Vincent Tassion, Franco Severo, and Philippe Easo, where they give a new proof that PC is less than 1 for dimension bigger than 2. And one thing that they show there is that if the probability that I manage to connect, if I have some set and I have the boundary, the probability that I manage to connect it is essentially I only need to pay exponential in the boundary of the set. I don't need to pay anything more in vertex transitive graphs boundary degree. So essentially what you would do is you would try to connect up this, graph, you connect up this set, and then you would close its boundary. So it's really up to this phi of n. can always look at the worst one, connect it up, and close the boundary, and this is essentially what it would cost you. So you really care about these iso-optimal sets.
And this is very similar to the repulsion ideas you said, right, of Tom Hutchcroft and his.
Yeah. So Tom Hutchcroft really, when this particular type of argument. So Tom Hutchcroft also goes back to Gabor Peter, and they have this argument, a really beautiful argument. But there, one of the key things they show. So what they actually show is that if you prove what Tom showed, is that if instead of proving this, if you prove that this probability is at least some constant, then you are in business. And one key observation that we had is that you don't need this probability to be some constant. It's actually enough that this probability is exponentially small, but not too fast, exponentially small. So Tom showed that if this is constant, then you're in business. In fact, pretty much the same argument tells you that if you're not too far from, if you're exponential but arbitrarily slow exponential, then you're also in business. So this is the only observation here. The key difficulty is really in showing this. And this is like, you need to flip the idea. You need to first find the right locations to look at. You need to first do low density in order to see whether they are safe. And if they are safe, only then you reveal the big information around them.
I see. Very nice, yeah.
Thank you.
More questions, Avelio or someone else there?
Not for my part.
Write someone in the chat, no? No, seems not to be the case. Well, you want to say what's your future work plan, or is this solving everything now, or?
So one thing that's interesting, okay, FK is obviously a beautiful question here. We're also interested and we're trying to look at finite graphs of growing degree, or in general, you can ask this question, for example, for weighted infinite graphs. So that it will also apply to long-range percolation, for example. And there are some challenges. We think we are able to do this, but there are some challenges that it's not, like, for example, you cannot take this, like here we have the seed being a ball. It makes no sense to take a ball in a high degree graph, also in long range percolation. It's not the thing you would want to do. So you need to do something a bit different. And there are other subtleties that you need to deal with, but the key idea hopefully does work. It seems at least that it works. So that's one thing to move forward. Obviously, trying to understand like this, we go back to the theorem itself, trying to understand what this constant is, what's the best you can get from this proof, trying to make it quantitative. This could be a step towards understanding or moving closer to understanding the behavior in the criticality itself. But that's obviously very, very, very hard.
Okay. Well, if there are no more questions, then let's thank Sahar again.
We are sorry we cannot send you a coffee. We are a little bit we owe you a coffee.
That's all right. That's fair enough. Yeah, how's the coffee in Chile? Is it good?
The one here is not, so you are safe.
I see. I didn't lose too much.
You can get good one in the university.
I see. I didn't lose too much. I can probably guarantee you that compared to the average coffee in Switzerland, it's quite good. But
maybe
I guess
a bit
that's
more
not a hard game.
expensive. A bit more expensive.
Yeah,
but
yeah. Yes.
Yeah, no, I feel better with my coffee here because I pay so much.
One espresso in Switzerland.
Yeah.